Section 5.3, spanning trees. We're gonna make 2 videos for this one. The second video will be looking at Preem's algorithm. Otherwise, we're gonna look at spanning trees for this first video. So when we talk about the traffic engineers from previous sections, kind of bringing that conversation back up, we wish to reach all vertices of a graph, but also wish to plow a small number of road segments. They determined that finding a tree within a graph will help them solve their problem. And so it's kind of establishing like, why do we use this? What's the purpose? So what is a spanning tree? The spanning tree of a graph G is a subgraph of G that includes all the vertices of G. It also has a tree. So let's take a minute and pause and think about that for a second. So we're not losing any vertices, and it also is a tree. So we're spanning all of the vertices of the graph, but the main thing we're doing here is we're taking away the fact that it's not connected. So let's go back and look at a couple other notes here. A tree has no cycles. So remember, a cycle is something that starts and ends at the same vertex. And so we know that if we're going to be a tree, we don't have that ability to start and end at the same place. So a tree has no cycles. We can find a spanning tree for a connected graph by discarding edges that are part of cycles until we are left with a subgraph that has no cycles. So let's take a look at this. So in this particular example, we start off and we're like, we want to make a spanning tree. So we want to have all the vertices, but we don't want it to be connected. So we can't cycle through. So we start off and we arbitrarily choose, we could choose AB or AC, it's really up to us, but we delete, let's say AB. So now AB is gone. And at that point, we're kind of moving across, we're trying to figure out like what else can we eliminate at this point because we still have cycles going on here. So we discard CD. And so we see up here on figure, the second figure up here, we remove CD. All right, so now we're taken away, but we still have a cycle inside of here. We still could go from C, D, E back to C, B, excuse me, E back to C. So to finish off, we remove BE at the very bottom. So now we have a tree because the tree has no cycles in it. So we have the inability to start at one place and cycle through without traveling over edges more than once. And we can see that the resulting subgraph still has all the vertices of G, but it has no cycles remaining. The result is a spanning tree. And that's our figure 3. That's that guy. Now, the main thing to think about it here is the idea that, we could have started, and I kind of pointed that out, we could have started with any combination. So there's always going to be several ways that we could make a spanning tree from a connected graph like this. So there's not necessarily a right or wrong answer as long as we get to the end and we end up having a graph that is a subgraph of the original. It has all of the vertices, and there are no cycles remaining. So there's no way to cycle through. So that's kind of our main thing about a spanning tree. All right, so with this comes this idea of Theorem 8. And with Theorem 8, what we want to take into consideration is the fact that what if we had a large number of vertices? Like, here we're looking at a small number of vertices that we can handle ourselves just by eliminating and going through and visually seeing it. But if we had a larger number of vertices that we had to encounter, then we would have to use the theorem. And so the theorem says a graph is connected if and only if it has a spanning tree. So essentially, through this process, we would be able to eliminate and get ourselves down to a situation where we had a spanning tree that had no cycles, but yet all the vertices that we needed. So we could travel through all the locations. All right, so breadth first spanning tree search algorithms. There's just an algorithm to kind of help us. So for graphs with a smaller number of vertices, it's quite easy to find several spanning trees merely by inspection. But for larger graphs, you might be guided by Theorem 8 and find a spanning tree by finding a cycle and destroying them by removing edges. However, for larger graphs, like I said, it's important to have a more systematic algorithm. So here's one of them. So this is an algorithm that will help us. So we will give a geometric description for this algorithm that finds a spanning tree for a connected graph. All right. So starting us off here, we've got these steps. And so we're going to go through and do an example to apply these steps. But this will kind of just help you kind of visualize and keep in mind that these are the steps that we will follow with this particular algorithm. So initially we'll start off and we'll be at step 0 and we'll label vertex A step. So just step. That's our first spot. Then after that, we'll label all unlabeled vertices adjacent to the vertices labeled step with step plus 1. And then for each step, for each vertex V labeled step 1, you'll choose exactly one edge E that's incident with V and some vertex labeled step. And you'll shade that edge in its vertices and let that step equal step plus 1. So that's kind of confusing when you look at that. When we do the example, you're gonna be like, oh, that makes perfect sense. Until our vertices are shaded, return to 2, and otherwise the vertices and edges are shaded, form a spanning tree for the graph. So let's take a look what this looks like. All right, so here we go. So use breadth first search to find a spanning tree for the connected graph in 5. And so you can see that on the left hand, we will follow the iterations. Not sure why that's not grabbing for me. Sorry about that. On the left, we'll follow. Sorry. All right, on the left, we will follow the iterations of 2. So that's step 2 of the process that we have in the previous slide. So that's this right here, this guy. And keeping up with the values of step. On the right, we will draw the shade. We'll draw the graph, shade the vertices and edges as they are added to the spanning tree that's being built. So you can see here, we're at step 0. We've already gone ahead and put that step 0 on there. All right, so initially with vertex A labeled 0 as seen in figure 6a, the first iteration of step 2, step 0 is 0. Vertices B, E, and C are labeled step plus 1, or also known as 1. So 0 plus 1 is 1. So to go from A to B is 1, A to E is 1, and A to C is 1. For vertices B, we'll shade AB and its vertices similarly shade AE and AC. Our second iteration will continue on doing the same thing. So now it's step plus. So we're taking whatever step that we're on. So we're on step 1 currently. So we're going to take step 1 and go to step 2 essentially. So you can see that we go on A, B, and then B to D. And so we see 2 because that's our second. We've added 1 onto the step here to get 2. When we go out to E, E has 2 ways it can go. It can go to EF or it can go to EG. So both of those are labeled 2. And then, interesting enough, not real sure why we didn't go down there. Let me hit pause for a minute and take a look. Sorry about that. I actually have it right in here. So in regards to G, vertex G, we must choose between edges EG and CG because both of them are incident with G. And so we can either say CG to get the G or EG get the G. And so we just had to arbitrarily choose one. And so we chose EG. All right. So we continue on the process. That takes us to our last piece to get us to where we'll have a tree where all vertices are touched, but yet we have no cycles. And so we can go down the path of adding on and see that we have 3 will get us there. And once again, because FH and GH are both incident with vertex H, we just choose one arbitrarily or randomly and find out our distance there. And that gives us our spanning tree where there's no cycles. All right, so minimum spanning trees. The whole idea is going back. So this is the same image that I had in right here in the initial conversation, talking about the engineers and looking at the minimum distance that we can go. So in this case here, we're looking at a minimum spanning tree. It's all about the weight of the subgraph. So in a weighted connected graph, the weight of a subgraph is the sum of the weights of the edges. So you guess you could use this to as far as mileage. So if you had to travel between the different vertices, which could be locations, and you wanted to find the shortest route, this is what we'd use a minimum spanning tree for. So a minimum spanning tree of graph G is a spanning tree of G with the smallest possible weight. Now, the trouble with this is that, the fact that we talked about that when you have a very large size of a graph, what's going to end up happening is that you're going to have spanning trees for each iteration. And so with that, that creates a massive amount of work. And so in 1957, Robert Preem designed an algorithm that builds minimum spanning trees T edge by edge. And so this algorithm can be described as follows, where the T is the minimum spanning tree that we are forming step by step for connected graph G with vertices N. So we're going to take a look at that in the next video. So this problem of having minimum spanning trees was solved by Preem.